तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will talk about some timing issues in clocking flip-flops. In the last lecture we saw the different types of flip-flops, and we also saw that clock is an important component or input signal of the flip-flop. The flip-flop changes state, output flip-flop output changes state with the clock. It could be level triggered when the output changes when the clock is 1, or edge triggered when the output changes when clock edge transition occurs, either from 0 to 1 or 1 to 0. So whatever it is, the clock is a central signal around which the operation of the flip flop is designed, operation of the flip flop takes place, and we need to know how exactly it influences the performance of the flip flop. So in this lecture we will talk about some of the timing issues. I call this lecture the clocking of the flip flop. That means we will discuss all timing aspects connected to the flip flop operation. Let us take an example of a simple D flip flop, edge triggered. By the way, when you have an edge triggered flip flop, the clock is given a little arrow. This is a common practice. You may be familiar with this from your previous course on digital circuits. And if it is a negative edge triggered, you put a bubble, extra bubble in addition to the arrowhead. Output is Q bar. So this arrowhead indicates this is a positive edge triggered flip flop. That means what happens is, now this is the D signal, inputs D, which goes from 0 to 1 at this instant of time, but there is no clock, the clock is 0, so the output does not change. Let us assume the initial output to be 0, the output does not change, and when the clock goes from 0 to 1, and I assume this is a positive edge triggered flip flop, so when the clock changes from 0 to 1, the output has to now change from 0 to 1 also, because D is 1. Now this happens here, should happen here, but it happens here usually a little later because of the propagation delay. So this period is called TP LH, propagation delay from low to high. If the output has to change from low to high, the amount of time required for that propagation, that is called propagation delay, TP LH. Now likewise, when the flip flop clock is made to 0, clock is made 0, output does not change because output continues to be D, and next time the positive edge occurs, only the input will be looked at, and when that happens we see that the input is 0. D has already become 0 before the second clock edge, at which time the input signal will be transmitted to the output. That means the output Q will go from 1 to 0, again not immediately, with a little delay, called in this case what, TP HL. Propagation delay corresponds to the variation transition from high to low. Now, when you are talking about flip flop transitions, generally for typical values you will take the average of these two. In some cases we will take the maximum of these two depending on the type of operation. So, worst case delay is maximum of these two and typical value is the average of these two. This factor is important, that you should know before finding how fast, how frequently can you clock the circuit. Before you can decide that, we need to know these values. Now, the one other thing is, this is purely the output propagation, the propagation of the signal through the gates inside the flip flop to the output. There are a couple of more timings we have to be concerned about. One is called the setup time, the other is called the hold time. We will define this. When the clock transition occurs, we are already assuming in this case there is a D was a 0 became 1 much before the clock transition occurred. So, when the clock transition occurred, this 1 was transmitted to the output, of course with a propagation delay. What if D changes closer to clock transition? Instead of D changing from 0 to 1 here, suppose it changes from here or here or here. Is there any restriction or condition which says how soon or how early should D change before the clock edge arrives, in order for the clock edge to recognize this change and transmit it to the output? Something like, if you want to board a bus, how early should you be in the bus stop at the bus terminal before you are allowed to get in? You cannot just get into the bus and the bus is starting, because you are not sure, you may run into an accident, you may fall from a footboard, or because you do not know there are enough space inside. So, this is of course this is not a technical reason, but technically we will see how this. But what I am saying is, you should know before any activity we should be clear about the intention of the circuit. That means the circuit intention is the input has to change from 0 to 1, and that intention should be made very clear before the clock arrives, and how early should it happen. That is called the setup time. So, somewhere here this interval we will call this TSU, T setup. The setup time is the minimum time before the clock transition that the input should be stable, or the input of the flip flop. That is called the setup time. In this case, of course, this is an external time which has no meaning. So, I can afford to change my D here, 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 anywhere, but not beyond this point. Beyond this point, see, the problem is what will happen if you make it beyond this point. Supposing you let the D change here, can you positively say that this input will not be recognized? No, these are all typical values. It may or may not. What we can say is it is not guaranteed. The transition being captured by the flip flop is not guaranteed. But when you want a reliable operation of the flip flop, you do not want an output which is not guaranteed. Either you should say it is not changing or it is changing. Either way I am happy. If you say it is not changing, fine, I will try to do it next time. If it changes, fine, I will use this now. But if you say it may or may not change, that is a condition we should avoid in any design. because we do not want any unreliable or unpredictable performance. So, we have to avoid making D change occur here. We should never let this change of D anywhere here. We should make sure it happens before this. This is a condition. By the same argument, this signal to be captured by this, I said it has to be positive edge. When the positive edge or the transition from 0 to 1 occurs for the clock, D should be high, and not only it should be high at this point, it should be high sufficiently before. Now the question is, can I remove D as soon as the transition happens? Can I bring it back? Of course, in this case the D lasts so long, such a long duration. But if I say, is it alright if I remove D as soon as the clock transition occurs somewhere here? Again, is it acceptable? Now, there again there is a definition, there is a timing involved. There is a minimum time for which the output should be stable after the clock transition occurs for the output to be guaranteed again. This is all for guaranteed outputs, something like a quality. If you do not do it, nothing is going to happen, the world is not going to fall apart. The point is, you are not sure of the circuit performance. When you are not sure of the circuit performance, your output is not cannot be predicted properly. When your output cannot be predicted properly, your system is unreliable. I do not want to design an unreliable system, we do not want to design an unreliable system. That is what we will have to make every point, satisfy every point, every aspect of the timing. So, there is a minimum time for which the output should remain, input should remain stable after the clock transition occurs, and that time I will put arbitrarily here, beyond which D can change any time. There is no need for D to extend up to this point. It can go here down, it can go here down, it can go here down, and so forth. But this period is something which you have to, we cannot eliminate. This period is called hold time. So, now we have seen 4 timings, in fact 5 timings. I did not explicitly state the fifth one being the clock frequency. We are all trying to do all this to find out what is the highest frequency at which I can operate the system if necessary. Of course, I do not have to. When you are designing a traffic light signal in a major intersection of the roads, you do not operate in gigahertz or megahertz. You operate so that there is enough time for the cars to flow. On the other hand, when you are operating a computer, you work in terms of megahertz and hundreds of megahertz, and today in gigahertz. So, we should know these things. For example, some of these things do not matter in a system you may be designing. You may be designing a traffic light controller in which you are talking of milliseconds or even seconds as the minimum interval in which you are concerned, about which you are concerned. So, where is the question of a microsecond delay of the signal occurring, after the transition, and all that is not, it is a trivial issue. On the other hand, when you are designing a Pentium processor with, or any other microprocessor with 200 megahertz clock speed, we are talking of 5 nanoseconds the clock period, these things become comparable, numbers become comparable, then you have to be extra careful in your design. So, that is what I am trying to say, you will have to know all these things. The 5 things are involved. One is the clock period, the maximum clock frequency, which is implicitly told, I have not mentioned it, I have just assumed a clock waveform. And then there is this Q changing. There are 2 periods, one is called the transition propagation delay because of the transition from low to high, another is called propagation delay because of high to low, and the average of the 2 is a typical value, the maximum of the 2 is used for worst case designs. And then we are talking about 2 other terms, one is called the setup time, the period or the interval or the duration before the clock transition at which the input should be stable, and the hold time is the period for which the clock the input should be stable after the clock transition has occurred. So, let us write this here, TSU setup time TH hold time TPHL TPLH TPHL are flip flop propagation delays usually we take the average of these two as typical value, but I am going to define TP max as the maximum propagation delay which is the larger of these two numbers, greater of these two numbers, and TP min as minimum propagation delay. Which is the smaller of these two numbers. Then I will define the clock period T clock as the clock period. With these definitions, let us now write a couple of equations. T clock should be greater than or equal to TP maximum plus T setup time now. You see, naturally this TP maximum need not come into picture. What I am saying is the clock edge should occur setup time interval after the data change and hold time interval before the next data change. That means the data should change TSU before clock edge and should remain valid TH after the clock edge. Naturally we can get the frequency in terms of the clock period in terms of setup time and hold time, but I am deliberately introducing the P max TP max because sometimes what happens when you use a flip flop in a feedback mode, the output of the flip flop fed back as input to the same flip flop or some other flip flop, if the propagation delay is very small, because there is a maximum value, there can be a minimum value, there can be a typical value, these values may be smaller. When that happens, we do not want that to change the input before the hold time has elapsed. So, I want to write one more equation which will say TP min should be greater than or equal to T hold. But what I mean is if TP min happens before TH, that means if the propagation delay is less than TH, the output of the flip flop Q can go and change the input. That should not happen. The data should be valid because the data validity is what we are looking at. The valid data at the input of the flip flop should not change for a duration of TH after the clock edge, but after clock edge TP minimum is the minimum period at which the data is going to change, and if this is immediately fed back as the input, the data would have changed before TH has elapsed. So, that is why this additional condition. This additional condition comes about in order to make sure that the proper operation happens in case of feedback, which is many times done in sequential circuits. flip flop outputs are fed back as flip flop inputs for the next state or the next clock cycle. Otherwise what will happen is that generally we will have to say that T clock should be, so subject to this condition, that means that is why I put TP max here, otherwise we can simply say the clock period should be greater than T setup plus T hold. Because of that extra thing we are putting this. Now in practice though, the flip flop output does not get back into the flip flop input directly, there is usually a combination logic in between, there is usually a combination logic. So let us say there is a combination logic whose delay will define as T combination logic, that should be factored into this. So that means if there is going to be an additional time elapsed in propagating the output back to the input because of an extra combination logic through which it has to pass, it need not be the same flip flop. The flip flop of output of one flip flop can go to another flip flop through a combination logic. So that is the time T combination logic. My equation will now get modified as T clock should be greater than or equal to Tp maximum plus TSU plus T comb. Again we will say maximum because combination logic will not have all same delays. So maximum delay of the combination logic, maximum delay of the combination logic, and likewise this equation also will get modified as Tp minimum plus, so that means now we have a little, this is an extra restriction, there is this restriction gets reduced a little bit because I have the extra combination logic delay. What I said here was the propagation delay should be sufficient so that it does not reach the input in case of feedback before the hold time has expired. Now that I have an additional delay, that delay also can be counted into this. So what I have to say is Tp min plus, in this case I will say minimum combination logic delay, T comb min together should exceed Th. So these two equations are for a practical circuit in which generally outputs or flip flops are fed into the next flip flop through a combination logic, either to the same flip flop as a feedback output or a next flip flop through as an input to the next stage. In either case there will be a combination logic in between, that combination logic delay is also taken into account, in one case maximum value of that, another case minimum value of that. In this case it is just the flip flop alone. So these are the limiting conditions for the flip flop operation, proper flip flop operation of the. So how does it help us? We can find out what is the maximum frequency at which you can operate the circuit. Now Tc clock is a period, the frequency of a clock is inverse of clock period. So now the maximum frequency at which I can operate a flip flop will depend on the maximum, the minimum period of the clock, and that period determines the maximum frequency. So Tc maximum, Fc clock maximum will be 1 over Tc clock minimum, T clock minimum. And this is an important equation when you are designing a system. Flip flops have to operate at this speed. So, we have seen the different types of flip flops and the clocking requirements, the frequency of the clock and what is the maximum frequency at which you can operate the flip flop, etc. Now, let us see how do we use these flip flops in sequential circuits. As I said earlier, no circuit is entirely combinational. Most circuits, very few circuits can be fully combinational. That means most of the digital circuits or digital systems you design have both combinational and sequential components. A purely sequential circuit, what is a sequential circuit? Purely sequential circuit, a circuit is used only flip flops, something like a register or a counter. Even there you may have some resetting feature or some clearing feature and all that. But as I said, that may be a pure sequential circuit, very few of them, and a very few combination logic circuits, but most of the circuits are circuits which have both sequential and combinational elements in it, even though they are called sequential circuits. Any circuit which sequences through various clock periods, various states, and each state changes, states change with the clock period, such circuits are called sequential circuits. So, we have the typical representation of a sequential circuit as a block which is called the combinational block really, because as I said the combination logic, this is actually a combinational logic. And inputs to the combination logic and the outputs to the combination logic. Some of these outputs require to be stored and used later on. So, we may have two types of outputs for a combination logic. One is combination output, the other is outputs which are to be stored and reused. So, these outputs go through flip flops, because flip flop is a basic storage element and they need clocks. In a simple model we will use a D flip flop here, it can have any type of flip flop, it can be a JK flip flop for example. In that case we need a J input and a K input to be stored to get the next output. In this case we have a D, the advantage of a D flip flop is the input is the same as the output after the clock period. So, whatever you want to store will be directly put here. In the case of JK, in order to store something we need to find out the input combination of J and K, which has to generate the data 1 or 0 to be stored. So, let us make this simpler by making it D flip flop, making these D flip flops, they are clocked, we can have a single clock to clock both of them. So, let us call these inputs A, B, C, these outputs P, Q, R, and these flip flop outputs Q, of course there is a Q bar, which are normally required to be used again with another set of inputs, they are fed back. Maybe I would remove this. This is my, so let us call this what, X, Y. So, this combination logic has two sets of input. One set of inputs are called combinational inputs A, B, C are external inputs. Another set of inputs, in this case x and y, are called state inputs because they are internal inputs. These are the inputs generated in the previous clock period, stored and appear as inputs to the next during the next clock period. So, these are called state variables, x and y are called state variable, which determine the state of the circuit, state in which the circuit is in, and they will determine the next state x and next state y. So, the present state xy, present state of the variables xy along with the present inputs abc determine what should be the next state x and y. So, in order to distinguish between these two, usually people put a plus on this, x plus and y plus, indicating it is the next state. So, give a set of inputs xy which are the state inputs of the previous, during the previous clock period, I mean output of the during the previous clock period along with the combinational inputs ABC to get x plus y plus, which are going to be the next state inputs or outputs as the case may be, and PQR are the external outputs. These are called combinational outputs or external outputs. So, these are external inputs these are external outputs, these are state inputs, these are next state outputs. That means typically you give the present state inputs and the present state external inputs, you get the present state external outputs and the next state outputs, and the flip flops are used here. These are, that is why now this whole thing becomes a sequential circuit, which is have some practical meaning, which is A, B, C as the inputs. Maybe the in a traffic light controller situation, this can be the different sensors or timing elements, and it could be the state in which the circuit passes through, and this can be different lights, red, green, yellow lights which are required in the traffic intersection. So, this is how you have a normal sequential circuit or any standard digital system configured or defined. Combinational logic can be implemented, as you know, using gates or multiplexers or programmable logic elements, as we saw in our lectures on combinational logic, and these flip flops can be any type D or JK. As I said, D is simpler because the input becomes output next time after the clock occurs. There is one other variation of this input, this circuit, which is sometimes seen. Sometimes what will happen is the outputs, the external outputs are not directly from combinational logic, they combine the state outputs along with the combinational inputs. So, you will have a variation of this circuit in which you will have, for a change I will make it smaller on only one input. Just to give an example, only I am drawing this, so it does not have to be very complicated. Now, instead of directly getting the outputs, here this combines them, the output combines the state variables. Here we do not have this type of outputs here, these are directly used as outputs also. That means there are variations here, and variation in which the state input and the present input decide the external outputs, a set of external outputs and a set of next state outputs. That is one condition, one case. The other case, the combinational inputs and the percentage inputs decide the next state output, which also determines the output of the circuit. This variation is called a Moore's circuit. Where the outputs are tied to states, are not tied in the sense of any physical tying or electronic tying. Tied means outputs correspond to states. Outputs are defined for states. For a given state, an output is defined. No output can occur independent of a state. Here, there can be outputs which are based on the present state and the input variables, and such a circuit is called Mealy circuit. So, Mealy circuit, in which we will have a set of present state inputs and a present state variables, present state input variables and a combination of external variables, which determines not only the next state, but also the current output, current external output, combination outputs. Such a circuit is called a Mealy circuit. Both are possible in a system design. Here there will be outputs defined only for the states. Here the output will be defined for states occurring, for states and each state for any input occurring at that time. That is how it is defined. Now, whatever it is, we are going to use these elements. We have already seen enough of combination logic. Now, we have seen flip flops. So, connecting them together in this fashion realizes circuits. In order to do that, we need to go through a design procedure, which we will see in subsequent lectures. But I am just thought I will give you these two variations, and not only that, the basic architecture. That means anything, any digital system you are trying to design can be simplified or reduced to this format. What are the inputs? What are the outputs required externally? What are the state? How many states are required? Based on that, state variables are defined, and the present state variables along the inputs design the next state variable, etc., etc. This is a standard procedure that gives a lot of design methodology, which we will adopt in the subsequent lectures in order to design different types of digital systems. Now, I want to go a little out of this. We will come back to the design of the digital systems in this format using flip flops and combination logic. When you use the same clock, because in this case all the flip flops are clocked at the same time, only one stage of flip flops. Assuming that these outputs go to another similar circuit and we are going to clock this also, we work like a sort of a stage by stage pipeline. There are several stages. Supposing your circuit has several stages of sequential circuits, and all of these stages have flip flops, and output of one stage acts as the input of the second stage, input of the second stage acts as the input of the third, output of the second stage acts as the input of the third stage, and so forth. When the output of the first stage is decided, let me put it in as a sort of a graphical way. Supposing my system has several modules or subsystems, these may be sequential circuits, or as I said, digital system containing both combinational and sequential. So, there is a clock which is connected to all of them. Of course, there are inputs which realize outputs. There may be external inputs, and this can go into this, another input, go back, and then it can go back here if you want. All that is. The problem is these clocks should all be synchronous. they should occur at the same time. If I want to transfer this input, this output into the input of this, at the same time I should have transferred this output of this into the input of this. So there must be perfect synchronism between all the stages. So that can happen only when the clock edges, there should be no delay in the clock path. All the clock edges should be so perfectly synchronized, they should all be clocked at the same instant of time. Okay? That is one thing you need to know. So we need to know a couple of these things before we can proceed in our design. So let us state some basic rules. Clocking rules. No delay element should be put in the clocking path. The clock path. That means if I had a delay here, the clock period at which the instant at which this transition occurs is not the same as the instant at which this transition occurs. That means this output is delivered here, but this has not, this input has not been transferred. That means there is going to be a contention here. So the overall this is a very simple statement. People define something as a clock skew. Clock skew is a term which is used for non-uniform or non-synchronous distribution of clock. Non-synchronous clock distribution. All the clocks should appear at the same time in all the modules. What does not happen? One of the reasons of this is a clock skew. I will not put it as clock skew. One reason. Clock skew. Okay, that's all right. Clock skew is one of the reasons for which is not non-synchronous clock distribution. Other thing is this delay may be purposeful or unequal matching of the flip flops and all that. So whatever is the, you can put a deliberate delay. You can avoid that. No delay element should be. So second rule is avoid clock skew, which is part of the first rule. Avoid clock skew. Then we have to the extent use only synchronous sequence circuits. What do you mean by this? That means a sequence circuit is defined as a circuit in which the output is fed back along with the input, and we have the clock to determine when this input set of inputs, the new set of inputs is going to be recognized by that flip flop. Now suppose there is no clock, and just assume that this is a combination logic in which there are some inputs and then some outputs. Some other outputs are fed back without any clock, no clock. Is this a sequential circuit or not? By definition of sequential circuit, this is a sequential circuit. A sequential circuit is a circuit in which outputs are determined by the present outputs are determined by the present inputs and the previous outputs. The previous output is fed back into the gates, which will again affect the present state. So this goes on. Now there is no control when these things will happen. It all depends on the path delays, the delay path of the combination logic inside, that will determine. So, there is going to be a chaos inside this, chaotic, when especially when more than one input changes at the same time, the circuit behavior is not completely controlled by us. This is a problem. This problem can be avoided only by putting a clock. The clock, if you have a clock, the transition will occur at a given time. So, why can't we have a clock? Always have the clock. Sometimes the clock slows down the operation. Suppose I want as fast as possible. This circuit is called asynchronous sequence circuit. Asynchronous sequence circuit. That means a circuit which is a combinational circuit, I mean a sequential circuit, but there is no clock control. That means inputs can change any time, output can change any time. Based on the output change, input can again change. That can again trigger another set of output changes. That can trigger another set of output changes. This goes on and until the circuit stabilizes. Of course, there are some rules by which you can work with it in a satisfactory way. This is done in extreme cases where your speed of operation is so important, or because you have no clocking strategy between you are designing two circuits which are totally independent of each other, where there is no common clocking scheme. Your clocking scheme is different from the circuit to which you are going to interface. The clocking scheme of that circuit is going to be different from your clocking circuit, your clocking scheme. All these reasons, there may be several reasons why you may have to go for asynchronous sequential circuit. That has to be avoided if you want all these problems. Of course, if this is a special case, we have to go through this. This is a, I am not saying do not do this, do it with extreme caution, only under required conditions. Only when it is extremely important to go for asynchronous design, you go for asynchronous design. When you do it, it has to be carefully designed, go through a set of rules which are independent, which are totally different from the set of rules we are used to in the clocking scheme, and that this is not in the scope of our present lecture series. So, we will not talk about this, but you should know. So, what I mean by is that means the rules are to rewrite them. This I have just sort of haphazardly developed it. I am going to rewrite the same things. I will not even say clocking rules. Synchronous sequential circuits. Make them synchronous as far as possible. Two, do not put any delay element in the clockings. In the clock path. 3 I said clock skew, avoid clock skew. Clock skew can be part of this. So, clock skew could be the result of this also, but also there may be other reasons. That is why I am putting it as a separate case. Even though this is contained in this, there may be other reasons of clock skew. Avoid it if by proper design. By proper design. So, what we will do next is, of course, this is the rules we will follow in all our designs, and what I am going to do next is to give you certain cases in which I cannot, as I said, started with, we cannot afford to have this series of flip flops in a big circuit. This is going to consume a lot of real estate and lot of power consumption. So, is there a simpler scheme of getting flip flop implemented in IC? So, in my next lecture, we will talk about some flip flop implementation schemes adapted in integrated circuit design.